All right, let's just dive right in. We all kind of walk around thinking of space and time as, the background, the stage, the arena where everything in the universe happens. But what if it's not? What if that stage itself is actually built out of something else, something way deeper and weirder?
And look, this isn't just some abstract thing for physicists to argue about. This is a real question that someone asked on Reddit, and it gets right to the absolute heart of a huge mystery. Is this idea profound or just plain delusional? Well, let's find out. But before we can even touch that, we have to get on the same page. When a physicist says a word like fundamental, what do they actually mean? Because it's a big deal in their world. Just think about how we've tried to find the building blocks of matter. For the longest time, we thought atoms were it, the end of the line. The word atom literally means uncuttable. Then, of course, we figured out how to smash them open and found protons, neutrons, and electrons. So we thought, aha, these are fundamental. Nope, we smashed those open too and found quarks. Every time we think we've hit the bedrock of reality, it turns out to be made of something even smaller. That whole process of digging down, that's reductionism.
But there's another idea, a powerful one, that goes in the complete opposite direction. It's called emergence. And it's this beautiful concept that when you get a bunch of simple things together, they can create brand new, complex behaviors, properties that none of the individual parts had on their own.
The best example is a school of fish. I mean, you could study one single fish your entire life. You could dissect it, map its brain, whatever, but you would never be able to predict the incredible, swirling, coordinated dance that a whole school of them does. That beautiful pattern isn't inside any one fish. It emerges from the group. So the billion-dollar question is spacetime a single fish, or is it the whole school?
And what's wild is that questioning the nature of space isn't some new-agey sci-fi idea. Oh no. This is a debate that goes back hundreds of years, to the absolute giants of physics. So in one corner, you had Isaac Newton. His view is probably the one that feels right to most of us. He basically said, space is an empty box, a container. It's just there. It exists, and then we put stuff inside it. But in the other corner was Gottfried Leibniz, and he said, no, space isn't a box at all. Space is just the set of relationships between things. It's the distances, the directions, the connections. If you took away all the stuff, space itself would just vanish. This shows it perfectly. Is space the empty box, or is it just the web of connections between the objects? For centuries, this was just a cool philosophical argument to have over a beer. It was a stalemate. But now, quantum mechanics might finally be able to settle the debate. Yeah, for a long time, it was just philosophy. But today, a mind-blowing new idea suggests that Leibniz was actually onto something huge. And it proposes that those relations he was talking about, well, they might just be one of the strangest things in the quantum world: entanglement. Physicist Sean Carroll explains this new way of thinking perfectly. See, for decades, physicists have been trying to quantize gravity. They've been trying to take Einstein's theory of space-time and force it to play by quantum rules. But what if that's completely backward? What if, instead, you just start with quantum mechanics and see if space-time and gravity along with it just pops out? Okay, I know what you're thinking, because I thought it too. How in the world do you build the solid three-dimensional space we live in out of something as ghostly and abstract as quantum information? It sounds nuts, right?
Well, the recipe, believe it or not, is conceptually kind of simple. First, you forget about space completely. You start with this purely mathematical thing called a Hilbert space, which is just a way to describe all the possible things a quantum system can do. Then you chop up that abstract space into little pieces. And now, for the magic trick, you define the distance between any two of those pieces based on how much they're quantumly entangled. Now get this, because this is the core idea and it'll break your brain a little. In this new picture, physical closeness isn't the fundamental thing. Quantum entanglement is. So if two bits of quantum information are super entangled, they are, by definition, close to each other. If they have zero entanglement, they are far apart. That's it. Distance is just a shadow cast by the real thing, the network of entanglement. This connects to another famous, wild idea called the holographic principle. You know how a hologram on a credit card is a flat, 2D surface, but it creates a 3D image? The holographic principle suggests our universe might be like that everything happening in our 3D reality, including gravity, could be completely described by a quantum theory living on some distant, flat, 2D boundary. And that leads us to one of the most incredible, jaw-dropping ideas in all of science, ER equals EPR. Now, that's a fancy-sounding conjecture, but what it's saying is that two things we thought were totally separate are actually the same. EPR is about entangled particles, that quantum weirdness. ER is an Einstein-Rosen bridge, which is just a cool name for a wormhole, a feature of spacetime geometry. The idea is that two entangled particles might literally be connected by a tiny, microscopic wormhole. Entanglement isn't some spooky connection. It might be the very thread that stitches the fabric of spacetime together. So, let's take a breath. If we follow this rabbit hole all the way down, where do we end up? What does it actually mean for us if spacetime, the very fabric of our reality, is just an emergent property of quantum information? Okay, let's circle all the way back to that original question from Reddit. After going through all of this, where do we land? Is this whole idea profound, or is it just delusional nonsense?
Well, the answer, coming from the frontiers of physics, seems to be leaning really, really heavily towards profound. But, and this is a huge but, it is so important to understand what that means. Saying spacetime is emergent is not the same as saying it's an illusion or that it isn't real. Oh, it's real. You and I are living in it. It's just not the bottom floor.
The best way to think about it is with those analogies we started with. Atoms are totally real, right? But they aren't fundamental. They're made of quarks. Or think about water. A single H2O molecule isn't wet. Wetness is a property that only shows up when you have trillions of them sloshing around together. Spacetime could be just like that. A real, large-scale property that emerges from the chatter of countless quantum bits. And here it is. This is the real payoff, the grand prize. If geometry is just a picture of how things are entangled, then when you change the energy of a system, you change the entanglement patterns. And if you change the entanglement, you change the geometry. And what do we call the bending and warping of geometry in response to energy? We call it gravity. All of a sudden, gravity isn't the separate, mysterious force we have to jam into quantum theory. It's just what happens. It's an automatic, built-in feature of how quantum information works.
Which leaves us with one last, absolutely massive question to chew on. If spacetime is woven from the threads of quantum entanglement, and gravity is just a natural consequence of that fabric, does that mean our universe, at its very deepest level, isn't made of stuff at all? Is it just made of information? Is reality, at the bottom of it all, just one grand quantum computation?